thanks everyone for being here still, even if we're getting closer to the end of this conference. And I'm actually very happy that I can talk about these gauge fields today here at the conference organized by Gediminas, because actually I learned about gauge fields the first time from Gediminas in a cooperation with him. I will talk today about our project in Heidelberg, which is actually quite some effort on the experimental side here with a lot of young and very motivated students. And down here you see that we also enjoy really a lot of insight on the theory side in Heidelberg there. And if you look at them, these people here, they are all high energy theorists. And this is the specificity in Heidelberg, that we have actually a very strong high energy theory there and not so much the condensed matter. And this is actually how this project was born. And so when I arrived, I did not know anything about high energy physics. It's improving, but I'm an AMO physicist, right? And so when I first learned about gauge fields in itself, it was in a completely different context. And there was the idea, it was during my postdoc time, can we actually build very narrow tunnel junctions? And the idea was to play around with 3 level schemes, and then you can have these dark states in these level schemes. So, and the idea was if we can make the dark state composition change rapidly, then we might have a nice tunnel junction there. And we did lots and lots of calculations there, and we found these funny potentials. And at some point, actually, we talked to Gediminas, and he came around and he told us, look, it's a nice calculation, but you can open this review, which was published 2 years ago, and it's on page 4, and it's called the geometric scalar potential. So this was, by some accident, I actually learned that I did calculation on gauge theories, gauge fields, in a very different context, okay? And so we had this proposal, and actually it now even has worked nicely with ytterbium atoms at JQI, if you want to learn more. So this was my first contact with these gauge fields. The second way I think most people actually here at this conference think about them or had contact with is thinking about them as effective magnetic fields, right? We have these Hamiltonians where we put on a lattice some phase as we hop here. And if we engineer it nicely, we can have these flux lattices and then study all kinds of strong magnetic field physics. So here, this is a picture from graphene experiments where they do these measurements on strong magnetic fields, and they see somehow in these results the Hofstadter butterfly. And on the other side, you have the Hofstadter model as realized in the Munich group with an optical lattice. So this is the approach that I also knew until I was in Heidelberg, and then we started discussing in Heidelberg, and the things actually changed quite a bit. Because the theorists talked there about gauge theories, it was collider physics for them. So it really meant for them take 2 particles and smash them together at very, very high energy, and then look what are the resulting particles as they decay. And quite obviously for them, this meant that the gauge fields are here in these Lagrangian formulations. And it took actually quite some time to understand what this means. But the main thing is, as you smash these particles together, the decay or the particles created might be complex, but it's not some chaos. You have some really well-defined fundamental equations, which means that you have well-defined charges, which are locally conserved. You can't do anything, you have to follow these conservation laws, right? This is what they observe. And so if you have these local conservation laws, this also means that you have some local gauge symmetries. This is the idea as I understand it when I talk to the high energy community. So it always comes back that you somehow have to verify this Gauss law. So let's say that these circuits here are empty sites, and I put a little charge here in the middle, then the Gauss law directly tells me that the electric field has to point toward here, because the charge is there. What it also tells me that if I have a charge, and it hops, the electric field connecting the sides has to change too, okay? So really, like, whenever I discuss with them, it always comes about, show the Gauss law, and we can discuss about gauge theories. Otherwise, you don't have this local invariance, okay? So having these things is really important to show what they actually want to see in this collider physics, okay? So this is the first thing that we have to see. But now we have introduced these electric fields, which are seemingly, not super connected right now with the idea of these vector potentials that we typically look into. And I think that a very nice approach is this quantum link approach, to think about these little blurbs in the middle. And so the idea is then that you can think about the gauge field as a very, very long spin. And this very long spin is relatively close to the equator. And then the angle between the spin and this axis is actually the vector potential. And the z component of the spin is the electric field. Okay? So you move the spin away from the equator, stronger electric fields, and you rotate it, you have the gauge field. So now that we have this very long spin as a good idea for the quantum link approach, this is actually good motivation also to a good starting point to think about how we can do it in the lab, because long spins we can do there by using internal states. So what we have is we have sodium atoms, and we can use two internal states here, the MF0 state and the MF minus state. And then we put them, and the difference between is the Z component of this long spin, of this pseudospin system. And then we put them just on a lattice, such that we have these gauge fields locally on the lattice. Okay? So we have done this here now. This is a small system, but here are a few thousand atoms on each of these sides. And we can perform these Stern-Gerlach experiments to see how they are distinguished. And then, I mean, we can run two photon Rabi transitions such that we can really tune the starting point where all the atoms are in the minus state, and we get up to the 0 state. So we can tune the electric field. Okay? So this is nicely working now, but at this stage we actually have to see what is the Hamiltonian that we have to implement. So I gave you some kind of a Lagrangian, which is not the typical way how we like to think about it, or we used to think about it in AM physics. So now let me go through this step by step. So we take this Lagrangian thing, and we actually look at it in 1 dimensions. This has several advantages. The first one is that in 1 dimensions you don't have to implement magnetic fields, which makes everything much, much easier. The second thing is that these gamma matrices and this psi here only has 2 components in 1 dimension, which also makes things much easier. Okay. So this is this now, and if we don't have an electric field, we actually can take this thing here, describing the gauge field, and we see that after transforming into this Hamiltonian language, we can actually write it down as just some LZ squared term that we should implement. And this LZ squared term, well, this is what is known for us as the one-axis twisting Hamiltonian. The Oberthaler group has worked quite a bit on it already to perform squeezing experiments. So this is the first ingredient, but now we also need to implement the matter field, right? This blue part, and this matter field are lithium atoms in our case, and there are different ways of actually putting this thing on a lattice. And one of these things is like the so-called Kogut-Susskind Hamiltonian, where you have a staggered structure. So even sides are +1, odd sides are -1. Yeah. So this means, for me, looking at this, having a lattice structure which is staggered. And the idea is then to prepare the vacuum state, you fill up the lowest band there. And actually, quite nicely, the lowest filled band is really the Dirac that people talk about typically. And then creation of particles means that you take a particle from the lowest band and you put it in here. And left behind the hole is then called the antiparticle. So I told you that this is one way of discretizing the matter field. Another way of discretizing is actually using just this approach of a Hamiltonian, where you have on-site interactions between spin states, and then you hop by flipping these things. Yeah. Why is this interesting for us? Well, one way is you look at it in a tiny bit different way, and the other way is now you have only a gradient to apply here instead of doing these staggered structures. The third thing, this was actually a very nice surprise to us, is if you look at like this and you rearrange it, then you see this staggered structure, which is the SSH model. And this is the nice connection that we have now that we study, we want to study dynamic gauge fields and QED in 1 dimensions, but somehow here we directly see the connection to this SSH model, which is one of the standard models to study topology. So we're increasingly thinking about where does the topology get in this high energy problems that we have here. So we had all these nice talks especially on Monday afternoon, and there will be more to come from the Hauke group in the next N weeks. We will see papers in preparation. So we now know how we want to do the electric field. We know how we want to do the matter field, but the most important thing is actually doing this gauge invariant coupling, right? So how can we do this? This is this part here, and if we translate it into the Hamiltonian language, we get these terms here. This tells you if you go from one side to another side, you have to take this link operator in the middle and flip its spin there, a bit down. This leaves the trace behind that you want for the Gauss law. And if we look at this in our system, actually, we know that this has a spin. This is a spin system. We also know that our lithium atom can be spin up and spin down. So these are just what we see down our spin-changing collisions. And we already prepared and tested this approach. So we prepare the lithium atoms in the lower state, the sodium atoms in the zero state, and then we wait and we can see actually the rise that we are looking for. However, you see two problems with that. First is that the rise is not very large, and the second problem is that the time scales are pretty long there. So this is actually the main effort that we are doing right now, speeding up these collisions such that we can have dynamics on reasonable time scales. All right? And so now that we know all the building blocks that we want and that we are working on what is actually the physics that we would like to understand, where is this particle production here? Well, the particle production actually is you have a vacuum, all the atoms are in the lowest band, and then the question is, Then the question is, can I crank up the electric field so much that at some point I create particles, antiparticles, that I have pair production here? Okay? So you could imagine that if this state, the initial state of strong electric field, has a smaller energy, larger energy than having created particle hole, then there will be a spontaneous production of this problem. And so you can write it down like this, and what you can really see is that there's a critical electric field for this process starting, and this is then a nice toy model of the so-called Schwinger pair production, which has not been observed yet in true collider physics. Okay? So this is a nice motivation there too. And so this brings me already to the end. I was twice as fast as normally. I'm very sorry for that. We have done some good progress on the components. We are working on them. We know that we have different ways of actually looking at the same system in one dimension to understand it a bit better. And now we would actually like to implement this little cartoon with atoms where we put in some light or electric field and try to see a matter production. So thank you very much.